Hello, my name's Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is module 15 of our Circuits 2 lecture series, where I talk about two-port systems and two-port networks. And so by now in the lecture series, I think we're fairly comfortable with the notion of dealing with a circuit as kind of a black box, let's say, where we've got an input and an output. And we've looked at kind of two ways of handling this sort of system. We've looked at the system in the Laplace domain, where we have some input voltage and some output voltage as a function of S. We've also now looked at frequency-dependent transfer functions, where our input is some sort of phasor and our output is a phasor. And we've defined our transfer functions both in the Laplace domain as the ratio of V out over V in, and in the frequency domain as the ratio of the phasor that we have at the output if we excite the input of our system with the phasor Vi. And this kind of black box sort of system is called a two-port system. Two ports because we have, as you can see, two ports, an input and an output port. And typically, this is fine, and we've used these two-port networks to analyze filters, for example, in our filter discussion. However, a filter doesn't just sort of stand by itself. We usually want to drive it with some sort of amplifier, and we also want to connect it perhaps to some sort of load. And so a good example of this might be where we have a digital to analog converter that's creating an analog signal that is based on some digital information. However, there's maybe some high frequency quantization noise in this signal, and so we want to perhaps use a low pass filter to get rid of some of that high frequency noise. But then of course, we don't want to stop there. We want to hook our system up to some kind of a load like a speaker, so we can actually listen to the signal that we're generating, for example. And so we want to be able to cascade these two-port systems. And when you cascade them, it changes how the system behaves. So for example, we have our, if we just look at our low-pass filter in the frequency domain, we can draw something like this. And we have our resistor and our capacitor and our input voltage and our output voltage. And we know by now, and this is very familiar, our transfer function is 1 over j omega RC plus 1. So we've seen that a lot. But now what happens when we want to hook our circuit up to a load, like we would, in the case of this speaker situation? So we would still have our low-pass filter, and our capacitor. I'll just erase that bit there. Oh no, actually I will make it bigger, because I'm going to do some analysis. And we hook up some load resistance to our output terminal, and then we want to see how this affects our output voltage. And so this then becomes our circuit analysis problem. And so how do we handle this cascaded system? Well, I guess, one way is to just do our, regular old circuit analysis. So we have some input current phasor. We have, and this is a capacitance, we have some current through our capacitor. We have some current through our load. And we can use Kirchhoff's current law at this particular node, and we can say, our input current is equal to the current through the capacitor plus the current through the load. Current through the input is equal to the input voltage minus the output voltage divided by resistance. Current through the capacitor is output voltage divided by its impedance, 1 over j omega c. And then current through the load is equal to output voltage divided by RL. Right, so we have an equation here in terms of the input and the output voltage. And if we then solve for the ratio of output to input, and we do all our algebra, we end up getting RL over j omega c, R1 RL plus RL plus R1. And sorry, that's R1. So we can do that, right? I mean, there's no problem with this, and this is the correct result. However, it kind of defeats the purpose of having this quote-unquote black box, right? Because the whole idea of having this black box is for us to sort of, not have to worry about the details inside the system and basically just sort of hook it up however we want and cascade a bunch of these black boxes together and build a system that way without having to do sort of an individual component analysis every time we hook something up. And basically the whole purpose of two-port systems and two-port network analysis is to allow us to do things like cascading two-port networks together. So we could have, a digital to analog converter, and maybe this digital to analog converter has a DC offset, and so we want to get rid of that DC offset. So we use a high-pass filter to get rid of the DC offset, and then we cascade that with a low-pass filter to get rid of all the quantization noise, and then finally we hook this up to a speaker. And so we do want to be able to cascade these systems together without having to sort of, pull off the lid of each of these boxes and do an individual component analysis, because that really sort of defeats the purpose of having this high-level systems view. And so what we're going to do is we're going to look at two-port systems and networks and two-port parameters and see how they help us do this. So two-port parameters are basically the way that we characterize the voltage and current at the ports of our sort of black box system. And this diagram shows the convention that we use when characterizing voltage and current at the input to our two-port systems. So voltage 1, V1 is on the left-hand side, V2 is on the right-hand side. The positive polarity is at the top, negative at the bottom. Current I1, by convention, is defined as going into the system, and current I2 is also defined as going into the system. And this is a little bit different because up until now in our lecture series, we sort of have been thinking about, port 1 as being an input port and port 2 as being an output port, so current would naturally be flowing out of it. But it doesn't necessarily have to be the case. Like, for example, we could apply a voltage source at the left-hand port and at the right-hand port and then feed the system from two directions. And so that's where this convention kind of comes from. Now, two-port parameters basically characterize the relationship between these four parameters, our two voltages and our two currents. And there's actually a bunch of different ways that you can define two-port parameters. And all of these different definitions for parameters have different names. So there's things like the Z parameters and the Y parameters and the hybrid parameters and the ABCD parameters. And each parameter has advantages when we're connecting two-port systems together. And two-port systems can be connected in a bunch of different ways. We can have series connections, parallel connections, and also what's known as a cascade connection. And the series and parallel connections in particular might not look the way that you expect. In particular, the series connection. So a series, when we think of, probably when you're thinking about connecting these in series, we would have one system connected right next to another system. And that's actually, now that I'm talking about it, that's actually what we call the cascade connection. So if we have system A and two-port system B, and we just connect them like this. This is not a series connection. This is what's known as a cascade connection. The series connection actually looks kind of unusual if you're not familiar with it. We have our two-port parameter, or our two-port system A on the top, our two-port system B on the bottom, and we hook them up like this. So that's what a series connection looks like. So I guess you can think of them as kind of in series, with the top flowing into the bottom. Now, something I should point out that is in common for both the cascade and the series connections, whenever we connect two-port systems together, we create a bigger two-port system. So for example, if I was to put a dotted box around our cascade connection, we could represent that as a single two-port system with one port here and one port here. Same with the series connection. If I were to draw a dotted box around it, then this whole thing would be just one two-port system, and these two terminals would be our first port, and these two terminals would be our second port. Finally, it is also possible to hook up two systems in parallel. So we start out just like we did with our series connection, or with the same kind of orientation as our series connection. But then we take our first input terminal connected to the top of A and B. Our second input terminal is connected to the bottom of A and B. Our top of our output port, or sorry, not our output port, our second port is connected to the top of A and B, and the bottom, and so on. And so again, if we draw a dotted box around those parallel connections, we have one big two-port network with this as our first port and these two terminals as our second port. Now, I mentioned that what or sorry, I mentioned that there were a number of two-port parameters, Z, Y, hybrid, A, B, C, D. And the question is, well, which one should we focus on? Which one should we use? It turns out that the type of parameter that you choose depends on the manner in which you're going to be connecting your two-port systems. So for example, if you're connecting your systems in series, as I've shown here, the Z parameters are really convenient because the overall Z parameters for this interconnected system is just the sum of the Z parameters for A and B. If you're connecting them in parallel, the Y parameters are really convenient because the Y parameters for this overall system is just equal to the sum of the Y parameters for A plus the Y parameters for B. These two, I won't be talking in any more detail about series and parallel connected systems. Instead, what I want to do with the rest of our module is focus on the cascade connection. And the reason for that is because the cascade connection is a little bit more useful when we're thinking of, sort of filtering, audio, signal processing kind of applications where we have, as I drew it on the previous page, maybe a digital to analog converter and then the cascade of a couple filters before we connect to a speaker, or maybe if we connect to an antenna if we're doing kind of a wireless application. And so it turns out that if we're going to be cascading two-port systems, that the ABCD parameters are the most convenient to work with. And so that's what we're going to be focusing on. I won't be talking about the other ones, but just be aware that the other ones do exist. And if you find yourself connecting two-port parameters or two-port systems in other ways, that you can look into those and they might be easier for you. So ABCD parameters are also known as transmission parameters, and they do actually take the perspective that we've kind of been taking all the way through this lecture series, that the left-hand port is an input port and the right-hand port is an output port. And so what I'm going to do is I'm going to define my voltages and currents as phasors, because we're going to be assuming that our two-port systems have frequency-dependent transfer functions, or frequency-dependent components at least. And then we're going to define I1 as going in, which is just like we did up here. And then we're going to define I2 as going out, like it would for an output, but we then put a negative sign in front. And that's because just, normally for two-port systems, they're defined, current is defined as going in. So if it's coming out, then it's the negative of I2. Okay, so I mentioned that the whole point of two-port parameters is to indicate the relationship between the voltages and currents at the terminals. And we do this by way of an equation. And the equation for the ABCD parameters or the equations, there's two of them, are as follows. V1 is equal to A times, actually I'm going to not write that as a phasor. V1 is equal to A times V2 minus B times I2, and I1 is equal to C times V2 minus D times I2. Now it's got not, whoops, sorry, that should just be a regular D. In general, A, B, C, and D can be complex numbers, and they often are. However, I'm not drawing them as phasors because they're not, I'm not drawing them as bold because they're technically not phasors, right? Like they don't represent sinusoids, but they can be complex numbers. And so it's not going to be immediately obvious when you first see this, like, where did these equations come from? Why is it V2 and I2 on the right-hand side? Well, as this will become obvious, I guess, as we or more obvious as we work with them. But the first thing I want to point out is that we can write these two equations in matrix form, and this is going to be very useful for us actually. And when we write them in matrix form, we have our phasors V1 and I1 being equal to a 2 by 2 matrix containing our 4 complex numbers, A, B, C, and D, multiplied by a vector V2 and minus I2. So this is basically just the matrix multiplication. And maybe now you can sort of see where this is coming from a bit, because we basically have our input vector and our output vector, right? And then we've got our 4 parameters. And if we do a matrix multiplication of our output vector with these 4 parameters, we get our input vector. And so this is, again, meant to characterize the relationship between this vector or the numbers in this vector and the numbers in that vector. And what will sometimes do is I will represent this ABCD 2 by 2 matrix using a letter T with a little line above it, and the line above it just indicates that that's a matrix. So our next job will be to solve for, or to at least present the method for solving for the values of A, B, C, and D. And we determine these numbers basically by changing the voltages and currents that we apply to the input of our 2-port system. And so we very much, and this can actually be done using analysis, like using mathematical analysis, which is what we're going to be doing on paper. But you could equally do this with an actual physical 2-port system that you have in the lab. Maybe there's some kind of system you're not exactly sure what's inside, or you do know, but you're not exactly sure how all the components are going to work together, or maybe you know how they're supposed to work in theory, but in practice it might be a little bit different. And so you can actually experimentally determine these 2-port parameters as well. And this goes not just for ABCD parameters, but for any 2-port parameters. And so I'm going to try to present both perspectives. I'm going to show how we solve for A, for example, using analysis. But then I'm also going to draw a picture to show you how you would actually characterize A in the lab. And to help us with this, we're going to work with an example network, or an example 2-port system. And our 2-port system is basically just going to consist of 3 resistors hooked up in kind of a T network. Oops. R1, R2, and R3. And if we were to draw a black box around this system, it would look like that. And so I want to start by solving for A. And A has a name, and we refer to it as the open circuit voltage ratio, and you'll see why we call it that in a second. And so there's only one of our 2 equations that has A as a parameter in it. V1 is equal to A times V2 minus B times I2. And so if we want to figure out A, or solve for A, this second unknown is kind of, a bit of a hassle, so let's get rid of it. If we can configure or set up our circuit so that I2 is equal to 0, then this term falls away, and we can solve for A as being equal to V1 over V2. And then I'm going to use this notation to indicate that I2 is equal to 0. So A is equal to the ratio of V1 and V2 as long as I2 is equal to 0. And how do we make sure that I2 is equal to 0? Well, we'll just set up our network so that the output port is an open circuit, right? If it's an open circuit, then current can't flow. And so let's draw that. So here's our two-port network that we're characterizing. We want to solve for the value of A for this particular two-port network. R1, R2, and R3. This port is an open circuit, so no current can flow out of here. And we apply a voltage, V1, and we need to solve for the output voltage, V2. So now, because no current is flowing through this branch, there can be no voltage across this resistor. So V2 is just equal to the voltage across R3. And that means if I write the voltage across R3, since our output voltage V2 is equal to the voltage drop across R3, we can just use the voltage divider equation to figure out V2. So VR, or VR3, is equal to R3 over R1 plus R3 times V1, which is equal to V2. And so A, A is just equal to R1 plus R3 over R3. So in this case, A is a real number, and that's because there are only resistors in our network. If there were capacitors or inductors, A might be a complex number. And as it turns out, A is going to be our absolute favorite parameter. So we're working with these ABCD parameters for a bit here, and it's not immediately obvious how these are going to make our lives easier. But once we actually do start cascading our systems together, then we are going to basically use this A parameter to determine the voltage transfer function of a bunch of systems all cascaded together. But there'll be more on that later. Okay, so this is how we used our analysis, voltage divider and all that, to determine our parameter A. What if we were in the lab and this two-port system actually was a black box and we had to use our lab equipment to figure out our A parameter? What we would do experimentally would be to take our two-port system, and I'm just going to draw it as a black box. It could have our 3 resistors inside it, or it could have something totally different. And I'm going to connect port 1 to a voltage source, and I'm just going to draw this in terms of just regular DC voltages. We'll just assume that we're not working with phasors here. And our output port 2 is open circuited, but we need to know this voltage, right? Because A is equal to V1 divided by V2. We know V1 because that's the setting of our voltage source. We can measure V2 by hooking our output port up to a voltmeter. Now, voltmeters have a very high resistance to them, and so even though a very small amount of current will flow, it's such a small amount that it won't affect our measurement. And so this is where we get V1. This is how we measure V2, and then we can just take A as the ratio of those two values. So this is what you would do in the lab. All right, the next step is to solve for B. B is what we call our negative short circuit transfer impedance, and you'll see why it's a short circuit impedance in a second. Again, we're going to start by taking a look at the equation that contains B. Oops. A V1 minus B times I2. So in this case, we want to solve for B, and so this A term is a little bit of a nuisance, and so we want to get rid of it. And we can get rid of it by forcing, sorry, this should be V2, by forcing V2 to be equal to 0. And then once V2 is equal to 0, B is just equal to the negative of the ratio of V2 divided by I2, under the assumption that V2 is equal to 0. And how do we make sure that V2 is equal to 0? We basically short out the second port. And so to draw our network, R1, R3, and R2. I2 is defined as going in to the port. That's the convention. If we included the negative sign in front of it, it would be going out. But because I don't have the negative sign there, it's going in. We short these connections together. How can current flow in if we shorted the connections? Well, remember, this is just basically a short to ground, right? And it is certainly possible for current to flow through a resistor when it's connected to ground. So that's no problem. Oh, sorry, I made a mistake over here. This should be V1. And then we apply V1 to our left-hand port. And so basically what we need to do is we need to solve for I2 and for V1 and or we need to solve for the ratio basically. So what I'm going to do is I'm going to define the voltage across, or actually, it might be a little bit more clear. I'm going to define the voltage at this particular node as VR. And so I2 is equal to minus VR over R2. Right? Because we've defined I2 as flowing from the right to left direction. So if this is a positive voltage, it would cause voltage to go from left to right. So that's why we have the negative sign. And we can determine the voltage at VR using the voltage divider equation, but taking into account the fact that the second resistance is actually the parallel combination of R2 and R3. And so VR is equal to the parallel resistance of R2 and R3, which is R2, R3 divided by R2 plus R3, divided by, just because this is the voltage divider rule, the summation of R1 and the parallel combination of those two. So it's R1 plus R2, R3 over R2 plus R3. This whole thing is multiplied by V1. And then if we just take this term for VR and we substitute it into the numerator for our current, and then solve for the ratio of V1 and V2, we get B being equal to R1, R2 plus R3 plus the product of R2 and R3 divided by R3. And you can do that algebra if you want to kind of reassure yourself. Just pause the video. Take this term, plug it into the numerator there, and then solve for the ratio of negative V1 over I2, and you'll get that result. So how would we do this if we were doing it experimentally? So experimentally, again, we would have our two-port network. And we have our ammeter. And our voltage source. So we would apply a voltage source V1 to our terminal on the left. That's how we know what this voltage is. We would short out our terminal on the right, but then we would put an ammeter in here so that we can measure the value of I2 going into our circuit. The reason why it's okay to put an ammeter in here is because the internal resistance of a current meter is very, very small. The internal resistance of a voltmeter is really large, but the internal resistance of a current meter is really small. And so this basically still allows this loop to operate as a short circuit. So this is literally what we would do in the lab in order to characterize our B parameter. Okay, now let's solve for parameter C. So parameter C is called the open circuit transfer admittance. We are going to first of all write the equation that contains C in it. So this is our second equation, and it's equal to C times V2 minus D times I2. Just like before, because we're solving for C, we don't want D in our equation at this point. And so to get rid of it, we're just going to make sure that I2 is equal to 0. And when we do that, C is equal to I1 over V2 when we make sure that I2 is equal to 0. And we do that by making sure port 2 is just an open circuit. And so this looks a lot like the A parameter, right? This is the same sort of conditions, except we're solving for something a little bit different. R1, R2, and R3. We have our voltage source V1. We have to apply a voltage source. We're not interested in the value of V1, but we have to apply a voltage here so that we have a current flowing in, I1. We want to measure the voltage V2. And this is an open circuit so that I2 will be equal to 0. No current can flow there. And so I1 is very simple. It's just equal to the voltage we've applied across this input terminal divided by the sum of the resistances. So it's just Ohm's law, right? I1 is equal to V1 over R1 plus R3. The voltage across V2, because there's no current flowing through this resistor, is equal to the voltage across resistance 3. And VR3 is equal to R3 over R1 plus R3. times V1. So just voltage divider again. This is equal to V2. And then what I do is I just basically express V1 as being equal to R1 plus R3 over R3 times V2. I substitute it into there, and the result ends up being C being equal to 1 over R3. And again, I've skipped a few algebra steps here, so just if you want, again, pause the video, go through those steps, make sure that you can see how we go from these two equations to this one. But C is equal to 1 over R3. Now, if we were in the lab, how would we do this experimentally? Well, we would apply a voltage, V1, across our input terminals. We don't really care about that voltage value for this particular parameter. Instead, we care about the current. So we would put an ammeter or a current meter in series here so we can measure I1. We also need the value of V2. So we would measure V2 using a voltmeter. And again, the internal resistance of a voltmeter is high, so this still basically is effectively an open circuit. The internal resistance of a current meter is low, so having this, this instrument in series with our voltage source and our terminal doesn't really affect our measurement. So now finally, D, our last parameter, is something that's known as the negative short circuit current ratio. And again, exactly the same procedure. We first of all, we write down the equation that contains the parameter that we're interested in. I1 is equal to C V2 minus D times I2. Not interested in C, so I'm going to get rid of this by short-circuiting V2 so that V2 is equal to 0. And D then is equal to the negative of the current going into the port 1 divided by the current going into port 2 with the assumption that V2 has been shorted out. And so let's take a look at our network under these conditions. R1, R2, and R3. V1, we've got some current flowing into port 1, whoops. Should be I1, obviously. We short circuit our port 2 so that V2 is equal to 0. Then we also need to figure out the current I2 going into port 2. And in this case, we've got to do maybe a little bit more analysis. Let's define the voltage across R3 as VR3. Let's define the current going through R3 as IR3. Kirchhoff's current law says that with our currents defined as coming in, the current through R3 is equal to I1 plus I2. The voltage across R3 is just defined by Ohm's law. And it's equal to minus I2 times R2, right? And that's just, you know, the voltage rise across this resistor has to be equal to the voltage drop across R2 because this forms a loop. So this is just Kirchhoff's voltage law. Working, you know, these equations, we can write minus R2. So if we substitute IR3 is equal to negative R2 over R3 times I2. So if we substitute that back into here, I2 is equal to I1 plus I2. Then if we take this expression and we solve for the ratio of I1 over I2, and then we put a negative sign in front of it, we get D is equal to 1 plus R2 over R3. And finally, if we wanted to determine the parameter D experimentally, we would set up our lab equipment so that we would short circuit port 2, but we would keep a current meter in there. So we could measure the current flowing in to port 2, and then we would apply a voltage so we could measure the current flowing into port 1, and then we would take the ratio. Okay, so how exactly do ABCD parameters make our lives easier anyway? Up until now, that's kind of made our lives a little harder because we've had to learn how to calculate these different parameters under these strange situations. But the whole point of ABCD parameters is to simplify the calculation for cascaded systems to determine the overall performance of two or more cascaded systems. And so I've shown two cascaded two-port systems here, and I'm going to just write on the voltages and currents. And just for now, I'm going to drop the phasor notation just because it'll make our diagram a little bit too busy. But understand that these voltages could be regular voltages or phasors. So for our network A, at port 1, we have voltage V1A and current I1A going into port 1. Coming out of port 2 on network A, we have minus I2A, and our output voltage is V2A. At the input to B, we have an input voltage V1B and an input current I1B. At the output, we have a current minus I2B, and we have a voltage V2B. Okay, so we can write our ABCD matrix equations. The vector V1A and I1A is equal to the 2x2 ABCD matrix for system A multiplied by the vector V2A and minus I2A. I'm not going to write the 2x2 matrix. Instead, I'm going to represent this by the letter T with a little line over it. I'm going to give it a subscript A so that we know it corresponds to system A. Understand, though, that this is a 2x2 matrix. We can write the same equation for system B. V1B, I1B is equal to TB times V2B and minus I2B. Okay, so this equation is for the first system, this equation is for the second system. However, obviously when we connect these two systems together, we can start to make some equalities. So I guess if we note this, the first thing is that the voltage at the output of system A is equal to the voltage at the input of system B, and the current flowing out of A is equal to the current flowing into B. Whoops. Minus I2A is equal to I1B. So in other words, this vector is equal to this vector. And so we can write V1A, I1A is equal to TA times TB well, actually, I'll write this out a little longer, or a little bit more explicitly. TA times V2A times minus I2A. Right? So that's just the equation up here. But we can substitute in V1B for V2A and I1B for minus I2A. So we have TA is equal to V1B times I1B. But this vector is just equal to this product, so we can write this as follows. TA, TB, V1B, V2B and minus I2B. Or, in other words, if we want to draw, a big dotted box around our cascaded system and have V1A and I1A be our input and minus I2B and V2B be our output, our input vector is equal to a matrix T times our output vector, where our matrix T is just equal to the matrix product of the ABCD parameters for our first system and the ABCD parameters for our second system. And this is where we see the advantage of using these transmission parameters. So if we can figure out the ABCD parameters for our first system and our second system, when we cascade them together, we don't have to pull the lids off of both of these two systems and do like a component by component KVL or KCL analysis. Instead, we can just take the ABCD matrix for A, multiply it by the ABCD matrix for B, and we get the overall characteristic of our cascaded system. And this is really why we like to use these. However, this is, I can make this claim and demonstrate this demonstrate that this matrix multiplication works. But now what I need to do is I need to show you a few examples with some real circuits that we're familiar with to show you how these ABCD parameters make our lives easier. And so a good place to start is to remember that our objective basically all the way through this course has been to find the voltage transfer function of our circuits. Basically the output voltage divided by the input voltage. And so if we think of our large two-port network here, our voltage transfer function, h of omega, we'll just sort of steal this corner of the paper. Our voltage transfer function, h omega, if we think in terms of phasors again, would be equal to our output voltage, in this case, V2B, divided by our input voltage, in this case, V1A. Right? And so this is what we want to use our ABCD parameters to do. However, and so how do we do that? Remember that our definition for the parameter A was basically a voltage ratio, right? So A was equal to the voltage at our input divided by our voltage at our output, provided that we had no current flowing through our output port. And we're basically going to use this definition to find out what our voltage transfer function is. And so what I'm going to do is I'm going to very sort of explicitly write down the steps that we're going to follow for doing this. And then we're going to do two examples where we will actually perform this calculation, and you can see how it actually works with real circuits. Okay, so what is the procedure for finding the voltage transfer function of two cascaded networks when we're using ABCD parameters? Step one is always to figure out the ABCD parameters for each of our two systems. So we need to find out the ABCD parameters for system A, which we represent by the 2x2 matrix TA, and the parameters for system B, which we represent by the 2x2 matrix TB. We then perform a matrix multiplication. So T is equal to the matrix multiplication of TA and TB, right? And since this is a 2x2 matrix, this is a 2x2 matrix, the product T will still be a 2x2 matrix. We then pull the parameter A We pull the parameter A out of the upper left corner of this product matrix. And then basically, our voltage transfer function is equal to 1 over A, right? Because A is the input divided by the output, and our transfer function is output divided by input, and so we just take the reciprocal of those two. So what I want to do now is use two examples to show you how this works. Okay, here's our first example. So we are going to cascade this two-port network or two-port system with this two-port system. And of course, the first one, network A or system A, is just the T resistive network that we've been analyzing up until now. So I've taken the ABCD parameters that we've been working on and I've put them in the matrix TA. Our second network is just a load resistance, right? So basically I just want to take this load resistance and put it onto the network A. And this is a very common thing to want to be able to do, right? Remember when I was sort of motivating this whole thing at the start of this lecture, I said, well, it's nice to be able to, take a filter or something like that and then just put a load on the end of it. And so this is basically going to allow us to do this when we cascade with RL. So just very quickly, we're going to derive the ABCD parameters for this network. A is equal to the ratio of V1 over V2, given that I2 is equal to 0. So we have an open circuit. And because this is just a wire, the voltage across this terminal is going to be equal to the voltage across that terminal. So the A parameter is equal to 1. B is defined as the voltage V1 divided by I2, given that port 2 is short-circuited. Now, this is kind of a funny one, right? Because we've short-circuited port 2, so the voltage across here is 0. That means that the voltage across here is forced to be 0 as well. However, rather than, and if the voltage across here is 0, there's no current flowing, so this seems like it should be 0 over 0. However, the actual correct value for this is just 0. And the reason for that is it sort of takes the perspective that, even for an infinitesimally small voltage, like if we did try to apply a voltage here and the fact that this is just a wire, even an infinitesimally small voltage will cause basically an infinite current. And so we have something small over something super big. And so the parameter B is equal to 0. The parameter C is equal to the current I1 divided by voltage V2, given that port 2 is open circuited. I2 is equal to 0. Well, if this is open circuited, then the voltage across here is just equal to the voltage across here. And of course, the current flowing into our circuit just goes all the way through the resistor, and the current through the resistor is given by Ohm's law. So the current flowing through the resistor is V2 over RL. This is, on the denominator, we have V2. And so then this parameter just ends up being equal to 1 over RL. So C is equal to 1 over RL. And D is our current ratio. Oh, sorry, no, this is I1. Over I2, given that we've short-circuited the output. So if we short-circuit the output, no current can flow through the resistor, or no current will flow through the resistor. It'll prefer the short circuit. And that means all current will just flow through this top path and down the short circuit. So I1 is equal to minus I2, and this ratio ends up being equal to 1. Okay, to save us having to grind through all of the algebra, to just conclude this first example, what I've done is I've assumed values for each of the resistors, 100 ohms for R1, 200 ohms for R2, and so on. And then I've plugged those values into our ABCD matrices for system A and system B. And then the overall, so the first step in our procedure was to find the transmission matrices for our two systems. We've done that. The second step is to multiply those matrices together. And when we do that, we get 2.25, 0.0075, 366.67, and 1.67. So we're interested in finding the voltage transfer function, and as we pointed out in our procedure, our voltage transfer function is just equal to the parameter A in our cascaded ABCD matrix. And so h of omega, it's not a function of omega because we're just dealing with resistors for this first example, but in general h of omega is equal to 1 over A, which in this case is equal to 1 over 2.25 or 0.44. So that concludes our first example. Okay, so here's our two networks. Network A is our RC low-pass filter. Network B is our load resistor. We already know the ABCD parameters for the load resistor, and I've just put them there. So now let's find them for network A. So the A parameter for network A is the ratio of the voltage at the input, V1, divided by the voltage at the output, V2, assuming that the output is open circuited. And if this output is open circuited, then the output, or the voltage at the output is just one, or can just be found using the voltage divider equation and the complex impedances. So it's R plus 1 over j omega c divided by 1 over j omega c, or j omega, this should be R1, j omega R1 c plus 1. B is equal to minus V1 divided by I2, assuming that we've short-circuited the output. And this is just equal to minus V1 in this case over minus V1 divided by R1. The reason for that is when we short circuit this output, all the current is going to flow through here. None of the current is going to flow through the capacitor because it's shorted out. And then we basically have this resistor R1 shorted straight to ground. And so the current flowing through this branch, I2, is just the current flowing through the resistor. So that's why it's V1 divided by R1. And so this is equal to R1. And I'm going to say I am going a little bit more quickly through these ABCD parameters just because, we've kind of done this a few times now. However, if this is going too fast for you, feel free to pause the video. And if you want to, go back and do network A in exactly the same sort of careful step-by-step fashion that we did our very first example where we had that T resistive network. Just draw this circuit fresh every single time, have this open circuit or have it short circuit, and then sort of just carefully map out the currents and the voltages and make sure what I'm saying here is correct. The parameter C is equal to I1 divided by V2, given that we've short-circuited the output. And if I just draw kind of a mini diagram here, just so we still can sort of see exactly what we're working with. Sorry, yeah, this is an open circuit, so I2 is equal to 0, so this is an open circuit. So the total current flowing into the circuit is just the voltage V1 divided by the sum of the resistance and the capacitance. And V2 is just given by the voltage divider equation. So on the numerator, we have the current V1 divided by the sum of the resistance and the impedance of the capacitor. The voltage V across V2 is just the V1 times the voltage divider rule. 1 over j omega c over R1 plus 1 over j omega c. These will cancel, things will flip over, and this ends up just being equal to j omega c. And finally, the parameter d, the current flowing into the circuit, so the current flowing in this branch, I1, and the current flowing in this branch, I2, when we short circuit the output, is just equal, right? No current is going to flow through the capacitor if we've short circuited. So all the current is just going to flow through this branch, and then down. And so this ends up being equal to 1. And so our cascaded system then can be found by the matrix multiplication of these two ABCD parameters, j omega R1 C plus 1, R1, j omega C, 1, 1, 1 over RL, 0 and 0. And since I'm only really interested in the A parameter, right, in this product, what I'm going to do is I'm just going to take this first column and multiply it by the first row. So A then is just equal to j omega R1 C plus 1 times 1 plus R1 times RL. Oops, sorry, that's R1 divided by RL. Or if we put everything over a common denominator, j omega R1 C plus j omega R1 RL C plus RL plus R1 over RL. So I just took that and put it over the common denominator RL. And then H omega is equal to 1 over A, which is just the inverse of this, RL over j omega R1 RL C plus RL plus R1. And if you compare this to the expression that we had at the very start of this module, you'll see that this is the same, right? This is exactly the same result that we had when we did sort of our individual KCL and KVL analysis. And so hopefully this illustrates how this all kind of works and hangs together. And so, again, the whole point of, and the whole efficiency of ABCD analysis is that once you've figured out the ABCD parameters, you never have to figure them out again. It doesn't matter what system you're cascading it with. All you do is just perform the matrix multiplication, and then you can figure out the overall performance of your cascaded system. And in particular, if you substitute in numbers here, like we did for our resistor analysis, you can cascade, a huge number of matrices together if you're doing the matrix multiplication in a package like MATLAB, for example. And so that's really the efficiency of using these transmission parameters. Oops, sorry, I just caught a typo on this page and the previous page. The lower right-hand corner in the ABCD matrix for our load should be 1, not 0. And make that correction on the previous page as well. It didn't affect this example, right? Because we were just multiplying the first row by the first column in order to get the A parameter. But just to be strictly correct, or if you wanted to, for example, extend this matrix and cascade other stuff onto it, that lower right-hand corner parameter definitely needs to be a 1.